Here we have an uncompressed 5-second video, and it takes up 440 megabytes of space. And here, we have the same video, but compressed in an MP4 file, using H264 AAC. This only takes up 3 megabytes. Can you see a difference? What if we zoom in so we can see the individual pixels? In this video, we will investigate how the H264 and AAC algorithms compress video and audio so that the file size is reduced by over 100 times while maintaining almost no perceptible loss. We'll also examine how the video and audio tracks are represented with 1s and 0s and combined into an MP4 file so you could write a file yourself. But firstly, why is any of this important? Well, I've downloaded several dozen videos on social media platforms such as YouTube, Instagram, TikTok, and Reddit, and almost all of them were MP4 files using the H264 and AAC algorithms. In fact, this format of video makes up the vast majority of all videos found on the internet. And if you're anything like me, you probably spend hours every day watching videos on the internet. So, I think you deserve to know exactly how a video works. First of all, what is H264 and AAC? Both of these are codecs, short for coding and decoding algorithm. You can think of a codec like a type of film. Just as Technicolor, black and white, and slide film each have their own unique way of capturing and processing images, different codecs each have their own method of handling video and audio. H264, also known as AVC, or Advanced Video Coding, is our video codec, and AAC, also known as Advanced Audio Coding, is our audio codec. Now, there are hundreds of video and audio codecs out there, each storing the data in different ways. Neither H264 nor AAC have the best compression efficiency, nor do they take the least processing power to encode, but they seem to have just the right balance. So, how do they work? Well, let's start from the beginning. This is our video that we will be writing. So, we are trying to store a video. This means two components, the video and the sound. Let's start simple. Each pixel of the video will be stored with 3 bytes, one for red, green, and blue. 44,100 times a second, or around every 20 milliseconds, we measure the amplitude of our left and right speakers and store it with 2 bytes. This works perfectly fine, but it takes up a ridiculous amount of storage. To fix this, let's store our video and audio in a more efficient way. Let's split each frame, or slice, of our video into 16 by 16 squares. Each square will be called a macroblock. Let's focus on one macroblock from the first slice, which we'll call our IDR frame. Firstly, let's change the way each pixel is stored. Instead of using RGB, we will use a new color system called YCrCb. YCrCb stands for luminance, chrominance red, and chrominance blue. This splits each pixel into 1 Luma component and 2 Chroma components. Here is the mapping from RGB to YCrCb. The human eye is more sensitive to brightness than color. This is pretty easy to see because the CR and CB images look very bland compared to the Luma image. Because we've split the color and brightness components, we can use this to our advantage. We will apply Chroma Subsampling, or the reduction of the Chroma components. Let's apply 4-to-0 subsampling. This means for every 4 pixels, we have 2 Chroma samples, 1 red and 1 blue in the first row, and 0 Chroma samples in the second row. Start by dividing the Macroblock into 2 by 2 squares. For each 2 by 2 square, find the average of the 4 CR values and the average of the CB values. Previously, our 2 by 2 square had 4 Luma and 8 Chroma values, 12 total. Now, our 2x2 square will have 4 Luma values and 2 Chroma values, 6 total. We have already cut our file size in half. Here is our Macroblock before and after the subsampling. Next, let's try to remove redundancy within the 16x16 Luma component of our Macroblock. Our Macroblock is comprised of simple gradients, stripes, and patterns. So, we can extract predictable patterns and store only the small deviations. The first step is to find the best partitioning level and pattern, or mode, combination in a process called Intra Prediction. The two prediction levels are 16x16 and 16 4x4 squares. Let's start with the 16x16. There are 4 modes to test. To perform the prediction, we need to obtain reference pixels from the first row above, first row to the left, and the top left corner pixel from neighboring Macroblocks. Below is a table of Python code to generate our 4 predictions. After each mode, find the sum of absolute differences, or SAD, for each. Subtract the original value of each pixel from the predicted value, and add all absolute differences together. Then, set the best 16x16 mode to the one with the smallest SAD. If the 16x16 SAD is 0 or 1, we are safe to skip the next partition level to save time. But this is not our case. So, we move on to 4x4 modes. Divide the Macroblock into 16 4x4 blocks. Let's test 9 new modes to find the mode with the smallest SAD. Get the 8 pixels above, 4 pixels left, and the corner pixel for each 4x4 partition. Here is Python code to predict the 9 modes. After finding the best modes for all partitions, determine the one with the best overall SAD. This will be our final prediction. For each partition, let's also store a map of the differences from the predictions. These are called the residuals. For each pixel, subtract the original value from the predicted value. Numbers can be negative or positive. Now, we are left with 4 values. 2 8x8 Chroma blocks, the partition level, and a table of prediction modes and residuals. Next, we'll perform Intra Prediction on the 2 8x8 Chroma blocks. Since fine details in Chroma are less perceptible to the human eye, we'll limit our predictions to the 4 16x16 Intra modes from before, 0 DC, 1 horizontal, 2 vertical, and 3 plane, but applied over 8x8 pixel blocks instead of 16x16. Predict them together by finding the mode with the best combined SAD, so that we have 1 combined Chroma mode and 2 residuals. Congratulations! We have successfully represented our entire Macroblock as a set of patterns and residuals. However, our residuals are still quite large. Let's focus on reducing them. Let's say you hear this sound. The waveform of a sound measures its loudness tens of thousands of times per second. That's a huge number of values, but in reality, we don't need to store all of them. We just need to know which frequencies are present and how strong each one is. Instead of storing the entire waveform, we can summarize it with just a few values. A soft bass and a loud treble. It's like looking at a sound through a spectrogram or an equalizer. We can apply the same idea to images. Take a black and white checkerboard. It changes rapidly between black and white, which makes it a high-frequency pattern. Now imagine a smooth gradient fading from white on the left to black on the right. That's a low-frequency pattern because it changes gradually. In real images, high-frequency details include things like hair, grass, and text, all filled with fine, rapid variations. Low-frequency areas are smoother, like skies, walls, or soft shadows. Most natural images have lots of low frequency and little high frequency. The process described is called transformation. Let's first transform our Luma residuals. Make sure you have 16 residuals, each one being 4 by 4 pixels. In our case, we do, but otherwise, you'll have to subdivide your 8 by 8 or 16 by 16 residual blocks. Let's start by transforming the 4 rows. Start by representing each row like so: A0, A1, A2, and A3. For each of the rows, find the sum of the outer pixels, sum of the inner pixels, difference between inner pixels, shifts right 1 bit, and difference between outer pixels, shifts right 1 bit. Next, we'll find 4 frequency coefficients using a simple and reversible algorithm. Our 4 frequency coefficients are B0 equals S0 plus S1, B1 equals S3 plus S2, B2 equals S0 minus S1, and B3 equals S3 minus S2. Now, notice what happens to our frequency coefficients when we change the values of our row. A flat row, a smooth slope, slow ripples, fast ripples. By combining sums and differences, the transform captures different levels of detail in the residual. The coefficients reflect increasing complexity. B0 captures flatness, B1 captures first-order changes, B2 captures second-order changes, and B3 captures third-order changes. To finish the transformation, transform the columns based on the coefficients we obtained earlier. We are left with a 4 by 4 block of coefficients that have been transformed and transformed again. Here is the full transformation code. After transforming the Luma residuals, we do the same for the 2 8 by 8 Chroma residuals by splitting each into 4 4 by 4 blocks and then transforming those individually. Once you have those 4 transformed 4 by 4 blocks, you remove the first coefficient from each and gather those into a 2 by 2 block arranged like this: AB on the top row and CD below. Then, transform them into 4 coefficients H0, H1, H2, and H3 like so. We'll call these 4 coefficients our Chroma DC block. Meanwhile, the remaining coefficients in each 4 by 4 block, now without the DC coefficient, are referred to as Chroma AC blocks. Now, it's time to quantize the coefficients, a process where we multiply and right-shift them to produce smaller integers. This step is where the majority of precision is lost. The extent of this loss depends on the quantization parameter, QP. For this example, we'll use a QP value of 26. Here's how we'll quantize a transformed 4 by 4 block. First, find the remainder when QP is divided by 6, 2 for our example. Then, from these 6 multiplier tables, find the one which corresponds to the remainder. For each coefficient, start by finding the absolute value and multiplying it by the corresponding number on the multiplier table. Next, calculate the number of bits to shift right. Divide QP by 6, round down, then add 15. Perform the right shift. Finally, add back the original sign. To quantize our Chroma 4 by 4 blocks, bring the DC blocks back to the AC blocks. We'll quantize using the same method for the 15 AC coefficients. But for the DC coefficient, we'll use a separate method. Firstly, select the multiplier from this table depending on the QP. In our case, it's 162. Then, find the absolute value of the coefficient, right-shift the multiplier by 1 bit, and add these together. Finally, divide this by the multiplier, round down, and add back the original sign. Before quantization. After quantization. Now, we can finally begin writing to our file. After quantizing the residuals, most of our transform coefficients shrink down to 0, with only a few non-zero values surviving, mostly cluttered in the top left corner of the 4 by 4 block. This is because low frequency coefficients are stored there. As we move towards the bottom right corner, into the high frequency zone, the values get smaller, often being just 1s or 0s. To pack this data efficiently, we'll rearrange the coefficients so that the larger, more important ones come first. With a clever zigzag scan that snakes from the top left to the bottom right, we'll group large coefficients up front and leave our zeros and ones at the end. Reorder your original 4x4 block with indices like so. We've converted our video to Luma and Chroma, reduced the chroma, extracted out patterns, extracted the frequencies, reduced the coefficients, and ordered them with zeros at the end. Now, we are finally ready to write our file. We will use a complicated but highly efficient process called CABAC, or Context Adaptive Binary Arithmetic Coding, designed to extract all remaining patterns and redundancies out of our file. If you made it this far, then I would highly recommend that you check out the H264 specs I linked in the description, because things will get complicated from here. CABAC works by assigning probabilities to each bit based on its context. It does this through hundreds of context models, each tuned to the specific data element and constantly adapting as more bits are processed. Each context model is a set of two values, p_state_idx, an integer from 0 to 63, and MPS, the most probable symbol, a 0 or a 1. The first step of using CABAC is to initialize the context models. To allow for context to build up, we only initialize once at the start of each slice, so in most instances you can skip this. To initialize, we will use two predefined variables, m and n, and our quantization parameter, 26 in our case, to determine p_state_idx and MPS. The H264 specs gives a table of m and n values for each context model or ctxidx in tables 9-12 to 9-33. For each context, we first calculate init value using this formula. The floor of m times qp plus 8 divided by 16, then add n. Once we have init value, we make sure it stays within the allowed range, between 1 and 126. If it turns out to be less than 1, we set it to 1. If it goes above 126, we bring it back down to 126. Now, if init value is 63 or less, we initialize p_state_idx to 63 minus init value and MPS to 0. Otherwise, we initialize p_state_idx to init value minus 64 and MPS to 1. Like in machine learning, CABAC learns from previous bits to predict the next bit. To do this, it uses a coding interval, which starts big and uncertain and gets smaller and more certain as more bits match the most probable symbol. We'll initialize two more variables, code_i_low and code_i_range. Code_i_low, a 32-bit integer representing the minimum of the coding interval, is initialized as 0. Code_i_range, a 9-bit integer representing the range of the coding interval, is initialized as 510. The coding range, from code_i_low to code_i_low plus code_i_range, is split into two parts. The MPS range, usually bigger, and the LPS range, usually smaller. A third variable, bits outstanding, is initialized as 0. Now that we have initialized all variables, we can begin encoding. For each bit to encode, 1. Determine the MPS range and LPS range. In an ideal world, LPS range would be the coding interval times the LPS probability. However, this is computationally expensive, so we'll use a lookup table. To find LPS range, we'll need to find the quantized coding interval range index, qcode_i_range_idx. We can do so using this mapping. Next, reference table 9-44 in the H264 specs to map p_state_idx and qcode_range_idx to LPS range. Then, MPS range will be equal to the coding interval range minus the LPS range. 2. Adjust code_i_range and code_i_low. If the symbol to encode is the MPS, decrease code_i_range by LPS range. Code_i_low stays the same. If the symbol to encode is the LPS, increase code_i_low by MPS range and set code_i_range to LPS range. Update context model state. This step updates p-state-idx or the MPS certainty. Again, to avoid excessive computation, we will use table 9-45 of the H264 specs. Here is the mapping of p-state-idx depending on the MPS or LPS. If p-state-idx has lowered to 0, then we will flip the MPS. 4. Renormalization and bits outstanding handling. To maintain interval resolution, keep code I range more than 255. While code I range is less than 256, run this loop. If code I low is less than 256, output a 0. To output a bit. If this is the first time calling the output function, don't write anything. Otherwise, write the bit to the file. Then, flip the bit and write it to the file bits outstanding number of times. If code I low is greater than or equal to 512, decrease it by 512 and output a 1. If code I low is between 256 and 511, decrease it by 256 and increase bits outstanding by 1. Finally, multiply code I low and code I range by 2. Step 5. Repeat for next bit. After encoding all bits in the slice, the encoder first writes the CABAC termination symbol, a 1, to signal the end of intro decoding for the slice. If we aren't encoding the final bits in the slice, skip this step. This symbol uses the context model 276 and requires a special method to process. Decrease code I range by 2, then increase code I low by code I range. Then, set code I range to 2 and repeat the while loop we defined before. Output the 9th bit of code I low. Then, right shift code I low by 7 bits. Find the remainder when divided by 4. If the remainder is even, add 1. Finally, write this directly to the file. It is important to know that CABAC doesn't initially save space. Early in the encoding, it may even require more bits. However, as CABAC encodes more bits and adapts its context models, the compression efficiency improves significantly. As you will later see, our context comes from many different sources in order to increase efficiency. Occasionally, CABAC needs to be skipped to improve compression. In this case, the bits will be outputted with a special method. For each bit to encode, first, multiply code I low by 2. If the bit is a 1, increase code I low by code I range. Then, if code I low is greater than or equal to 1024, output a 1, and decrease code I low by 1024. If it's less than 512, output a 0. If it's between 512 and 1023, decrease it by 512 and increase bits outstanding by 1. Finally, 3 other encoding methods are commonly used: Unary, signed exponential golomb, and unsigned exponential golomb. To encode a number n using Unary, write n ones and add a 0. To encode a number n using unsigned exponential golomb, first, add 1 to n. Then, convert the result to binary. Next, count the number of bits, let's call it k, and write k minus 1 leading zeros, followed by the binary result. This creates a symmetric format where a single 1 sits in the middle, padded evenly by bits on the other side. To encode a number n using signed exponential golomb, first, find the absolute value of n, then double it. If n is less than 0, subtract 1. Encode the result using unsigned exponential golomb. When encoding with CABAC, the context model we use is made of 2 parts: the context index space and offset. Now that we have that down, let's start coding our macroblock. We'll start by writing our macroblock type. Refer to table 9-36 in the H.264 specs. Here we can see the 2 main types of macroblocks, the Intra 16x16 and the Intra n×n. If we're using Intra 16x16, here's how we'll find the correct macroblock type. The first suffix number is our Luma Intra 16x16 mode from 0 to 3. The second suffix number is 0 if all chroma residuals are 0, and 1 if the DC blocks have non-zeros, and 2 if the AC blocks have non-zeros. The third prefix number is 0 if any Luma residuals are empty, otherwise it's 1. If we're using Intra 4x4, our Macroblock type will be 0. We'll write each bit of our Macroblock type with the context model 3 plus bin IDX plus A plus B. A is 0 if the left Macroblock is unavailable, or if it was an Intra 4x4 Macroblock and our current context model is 3. Otherwise, A is 1. B is the same, but for the top Macroblock. The second bit is special, because it indicates if the Macroblock is compressed or not. It will use context model 276, which normally signals CABAC Termination. However, because we are using compression, we will use a different process. We decrease code I range by 2, then repeat the while loop we defined before. If we're using Intra 4x4, then for each sub-block, in left to right, top to bottom order, we'll encode the prediction mode by first finding the most probable mode, then encoding the current mode only if it's different. To find the most probable mode, we get the Intra Prediction modes of the top and left 4x4 block. If the top or left 4x4 block isn't available, or is part of an Intra 16x16 Macroblock, set its mode to 2, DC average. Finally, keep the one with a smaller mode value. Next, we write the previous Intra Prediction mode flag. This flag is set to 1 if the 4x4 block uses the most probable mode. We will use context model 68 to encode this bit. If previous Intra Prediction mode flag equals 0, it means we're not using the most probable mode. So, we remove the most probable mode from the list of 9 possible modes. Then encode the mode number from the 8 remaining modes using 3 bits. These 3 bits will all use context model 69. After this, we'll write our Intra Chroma Prediction mode using Unary, then limit it to 3 bits. Encode the first 2 bits with context model 64 and 65, then the third bit in bypass mode. Next, we write a coded block pattern, or CBP, indicating where residual blocks are present. CBP Luma has 4 bits, each corresponding to an 8x8 block, which contains 4 4x4 sub-blocks. If a bit is 0, all 4 4x4 blocks in that 8x8 region are assumed 0, and we skip coding the residuals. If a bit is 1, we then encode each 4x4 block individually. Encode using CABAC with context model 73 plus bin IDX plus A plus B. A is 1 if the left Macroblock is available and its corresponding 8x8 region is empty, and B is the same but for the top Macroblock. For our Chroma coded block pattern, we use the same logic as before. 0 if all Chroma residuals are empty, 1 if only DC residuals are present, and 2 if AC residuals are also present. Write this with Unary and limit it to 2 bits. Bit 1 will use context model 77 plus A plus B, where A is 1 if the left Macroblock is available and its Chroma blocks aren't all 0, and B is the same but for the top Macroblock. Bit 2 will use 78 plus A plus B, where A and B instead are 1 when the Macroblock's Chroma AC blocks are empty. Keep in mind that bits encoded with CABAC can be omitted, especially if they are the most probable symbol at the time. Now, we'll specify our quantization parameter, or QP. To save space, we'll only store the change in QP from the previous Macroblock using Unary. Because changing QP is optional, we'll write a 0 using context model 60. Finally, we move on to coding the 4x4 residual blocks, processing them from left to right and top to bottom. Any 2x2 groups of residual blocks marked as 0 by the CBP can be skipped entirely. In our case, none of the residuals are 0, so we must encode all 16 blocks. For each 4x4 block, we start by encoding a 1-bit coded block flag using CABAC to signal whether the specific block contains any non-zero coefficients. If this flag is 0, we skip the rest of that block. Since our flag is 1 for every block, we proceed to encode all of them. We will use context model 93 plus A plus 2B to encode this flag. Set A to 1 if the left Macroblock is available and its corresponding 4x4 Luma block is not empty. Set B to the same, but for the top macro block. So, we go through our transform coefficients one by one in zigzag order, and at each position, the first question is there anything here at all? If the coefficient is 0, we set significant coefficient flag to 0. If it's non-zero, we set significant coefficient flag to 1. Encode this flag using context model 134. Once we found a non-zero coefficient, we immediately want to know, is this the last one? That's where last significant coefficient flag comes in. If this is the final non-zero coefficient in the block, we set the flag to 1. Otherwise, it's 0. This flag is then encoded with context model 195. We can throw away coefficients after the last significant coefficient. Now, we'll find the absolute value of our non-zero coefficient and subtract 1. Write it in Unary and limit this to 14 bits. Encode this with context model 247. This is extremely rare, but if our value was over 14, then we'll subtract 14 and encode the difference in a special way. First, encode it with unsigned exp-golomb. Then, flip all the bits until the middle 1. Encode all these bits in bypass mode. Finally, if the coefficient was negative, set coefficient sign flag to 1, and if it was positive, set it to 0. Encode this 1-bit flag in bypass mode. In summary, for each coefficient, we peel back the information in carefully ordered layers. Is it non-zero? Is it the last one? What sign? Each of these decisions is encoded with either CABAC or without CABAC, depending on how predictable it is. The result is a remarkably compact and efficient representation. Next, we'll do the exact same process but for our Chroma DC blocks, starting with the blue, then the red. For each Chroma DC block, we first write a single coded block flag with context model 97 plus A plus 2B, where A is 1 if the left macroblock is available and has non-zero Chroma DC coefficients, and B is the same before the top macroblock. Next, our significant coefficient flags, last significant coefficient flags, and the truncated unary part of the coefficient absolute level minus 1 will use context models 149, 210, and 257. Finally, the same process is done for our AC blocks, blue then red. The coded block flag will use context model 101 plus A plus 2B, with A and B using the same logic as before. Our other three fields will use context models 152, 213, and 266. After completing our first macro block, we'll continue coding all others from left to right, then top to down. In total, we'll have to encode 3,600 macro blocks in our slice. Remember to include the CABAC termination symbol at the end. But wait! We still need a header so we can identify the slice. We'll put this before all of our macro blocks. Before we get into the details, let's figure out the different slice types we'll use. Firstly, the slice we just encoded will be called an I slice, which uses Intra Prediction. Then there's the P slice, which tries to predict stuff based on earlier slices, making it more efficient. B slices are a bit trickier since they predict both forward and backward, looking at slices before and after to get the best guess. B slices are completely optional, so we won't be using them. Recall from the very beginning of this video that the slice we just encoded was an IDR frame. An IDR frame is a special kind of I slice that says, from here on, nothing earlier matters. When we hit an IDR frame, the P frames are not allowed to reference any frames before it. Because of this, an IDR frame is always a key frame and contains only I slices. IDR frames are commonly found after a cut in a video to prevent this from happening. And for the same reason, the first frame, which we just encoded, is always an IDR frame. To save space, we will write some parameters in our slice header, and the rest in the sequence parameter set, or SPS, and the picture parameter set, or PPS. For now, we won't write them to our file. we'll use these parameters for our SPS, which works for almost all videos. The full format of an SPS is explained in section 7.3.2.1.1 of the H264 specs. Picture width in Macroblocks -1 is the video width 1280 divided by 16 minus 1. Picture height in map units -1 is the video height, or 720, divided by 16 minus 1. Log2 max frame number -4 is 4 less than the number of bits used to represent the frame number. 10 would mean the video can have 2 to the 14th, or 16,384 total frames, enough for a 10-minute video at 30 FPS. The frame rate is indirectly stored with a timescale and num units in tick. FPS equals timescale divided by 2 times num units in tick. Here is a typical PPS which works for most MP4 files. The full PPS format is found on section 7.3.2.2 of the H264 specs. Now let's get to writing our header. Slices don't live on their own. We will package our slice into something called a Network Abstraction Layer Unit, or simply NAL Unit. Let's start with the NAL Unit header. Always start by writing a 0. This way, we'll know that if our NAL unit doesn't start with a 0, the previous one is likely malformed. Next, we'll write 2 bits indicating the reference priority of our slice on a scale of 0 to 3. IDR frames get a 3, I frames get a 2, P frames get a 1, and if it's not a reference, it gets a 0. Finally, we'll write 5 bits, 00001 for non-IDR frames, and 00101 for IDR frames. Next, we'll use the following most commonly used fields for our slice header. The full slice header is defined in section 7.3.3 of the H264 specs. We'll set first macroblock in slice to 0. Our slice type will be 5 for P slices and 7 for I slices. Our picture parameter set ID will be 0. Next, the frame number is the current NAL unit being encoded starting at 0. IDR picture ID will only be encoded if this is an IDR frame, and it will be set to 0. Next is the picture order count LSB. This field determines the order that the frames are displayed. In our case, this will be the same as frame number because we aren't using B slices. Next is the no output of prior pictures flag. We'll set this to 1 if it's an IDR frame, otherwise 0. Finally, if this is a P slice, we'll encode the num-ref-idx active override flag as a 0. Next, if our slice type is P, encode is 0 to indicate that we aren't modifying our reference picture list. Then, encode our prediction weight table. First is the Luma log2 weight denominator. This determines the Luma weight position. We'll set to 5. Next is the Chroma log2 weight denominator, which determines the Chroma weight position, and we'll also set it to 5. After, coming from our PPS, for num-ref-idx L0 default active -1 plus 1 times, encode 2 zeros indicating that Luma and Chroma weights aren't modified. Next, encode the decoded reference picture marking. If our frame is IDR, then encode the no output of prior pics flag as 1, and the long-term reference flag as 0. But if our frame is non-IDR, then encode the adaptive reference picture marking mode flag as 0. Next, encode the following. Firstly, if it's a P slice, encode CABAC init IDC as 0. Next, slice QP delta, disable deblocking filter IDC, slice alpha C0 offset div2, and slice beta offset div2 are all set to 0. Now that we have finished encoding our slice header, make sure our slice ends byte aligned with the number of bits a multiple of 8 by adding RSBP trailing bits. Add a 1, then zeros until it is byte aligned. Finally, count the total number of bytes in our entire NAL unit and write it as a 32-bit unsigned integer before the NAL unit header. Congratulations! We finished encoding our first slice. Our next frame is a P slice. Like before, we'll write our NAL unit header but for P slices. Then, write the slice header. We'll follow the same steps as before, converting to YCrCb, then applying 420 Chroma Subsampling, and finally dividing the frame into Macroblocks. Instead of using Intra Prediction, we'll find matching blocks in previous frames and only store differences through a process called Intra Prediction. We first must decide our reference frames. By default, our reference frames will be the past 4 frames. But remember, we can't set reference frames before an IDR frame, so we can have anywhere from 1 to 4 reference frames. In our case, we only have 1, because this is the second slice. For P-frames, we will use more advanced partitioning techniques. We start with 4 main ways to split a macroblock: 16 by 16, 16 by 8, 8 by 16, and 8 by 8. If we pick the 8 by 8 option, each 8 by 8 block can be further divided into 8 by 8, 8 by 4, 4 by 8, or 4 by 4 partitions. Altogether, that adds up to 259 unique partitioning combinations for a macroblock. To keep things efficient, we'll stop searching early once we find a partition that looks promising. Also, we will only search with the Luma block and inherit everything to the Chroma blocks. Let's start with a 16 by 16 partition. Our goal is to find the best position in the best reference frame that matches our original 16 by 16 block as closely as possible. We'll call this position our motion vector. We'll first test these 6 positions in our reference frame. Note, if our macroblock is located at a corner or along the edge of the frame, any points causing the partition to fall outside of the frame boundaries are removed. Our second note is that our y-axis is flipped, with y values getting higher as we go down, and vice versa. For each of these points, we move our original macroblock center there and calculate the sum of absolute differences, SAD, to see how well that block matches. After finding the point with the lowest SAD, we repeat the scan again and again. Eventually, we'll find a motion vector that produces the smallest SAD of the 6 surrounding positions. Once this happens, we will use a smaller set of positions with these offsets to ensure we didn't miss any better centers. Once we again reach the best SAD, we will do one more test using 4 immediate neighbors, up, down, left, right, to make sure we didn't miss any spots. This will be our best integer position, but we don't stop here. We haven't yet tested subpixel positions. If you've ever played around with the digital art software, you may have noticed that at a very high zoom, the edges of your strokes don't look like your pen color. This is because at subpixel resolutions, the computer can only display a blend of the pen color and the background. We'll use this same concept of subpixel movements to create an even lower SAD. We'll start by testing the 8 surrounding half position candidates. Like before, our first step is to shift the reference block to each position. However, we obviously can't get the pixels at a non-integer position. One simple way is to reconstruct the reference block by setting each half position's pixel to the average of all touching pixels. Instead of just taking the touching pixels, we will use a wider range of neighboring pixels to create a better reconstruction. For each pixel in the reference block, do the following. Firstly, if a reference point's x position is non-zero, we will start 2.5 pixels to the left of our x position and get the 5 pixels to the right to leave us with 6 total pixels. Then, we'll multiply each pixel by its corresponding weight: 1, -5, 20, 20, -5, and 1. Add them together, divide by 32, and round to the nearest integer. If a reference point's y position is non-zero, then we'll start 2.5 pixels below our y position and do the same but vertically. If both our x and y were non-zero, then the reconstructed pixel will be the average of both processes rounded to the nearest integer. After we reconstruct the entire reference block, compare it with the original block to find its SAD. Once we've found the best half position, or none of the half positions improve the SAD, we move on to the quarter positions. Let's start with the quarter offset 0.250. This gives a full motion vector of -0.25, -1.5, meaning that our point is 75% of the way between the left and right pixel of the reference frame, and 50% of the way between the bottom and top pixel. So, our value will be 1/4 times 1/2 the bottom left pixel, 3/4 times 1/2 the bottom right pixel, 1/4 times 1/2 the top left pixel, and 3/4 times 1/2 the top right pixel. The process described is called linear interpolation, which essentially generates a gradient between 4 points. Once we found the best SAD for the 8 quarter positions, or none of the quarter positions improve the SAD, this will be our final motion vector for our 16 by 16 partition. If at any point the SAD drops below 4.5% of the maximum possible SAD, which is 65,280, we'll stop searching early to save time. We're using 4.5% purely for demonstrative purposes, but anywhere between 5 to 10% of the maximum SAD is a good stopping point. But if the 16 by 16 partition doesn't find a low enough SAD, we'll move on to the 16 by 8 partitions and repeat the search for both of those. If those fail too, we'll try 8 by 16, then 8 by 8, and so on, gradually using smaller partitions to get better matches. In our case, this was our best partition, and these were our best motion vectors, producing an SAD of 2,904. Because we only have one reference frame, we are done. But if we had more, then we'll have to repeat this process for all reference frames. Our Chroma components will inherit the Luma components partitions, but downscaled by 2 to fit the 8 by 8 size. We'll also inherit the motion vector, but divided by 2. To create our Chroma reference block, we will linearly interpolate between 4 integer pixels using the motion vector's offset. Note that the Chroma motion vectors will require a 1/8 pixel precision. Everything within a 4x4 partition will be put into one residual. Next, we'll split our residuals into 4x4 and do as before. First, apply transformation, then quantize, and put them in zigzag order. Now, we'll encode our macroblock. Because we used a different prediction method, we'll have to encode our macroblock differently. We'll start with a 1-bit macroblock skip flag. If this is true, the current macroblock is an exact copy of the same macroblock in the past frame. Encode it using context model 11 plus A plus B, where A is 1 if the left macroblock isn't skipped, and B is 1 if the top isn't skipped. Next, encode the NB type, and sub-NB type if NB type equals 3. Binarization is given in tables 9-37 and 9-38. For NB type, we will assign these context models to each bit, 17, 276, and 18. For the second bit, instead of CABAC termination, we'll encode it with normal CABAC, but we fix p-state IDX to 63 and the most probable symbol to 0. If needed, encode sub-NB type directly after using context model 21 plus bin IDX. We'll encode the 4 sub-NB types in this order. Now, encode the reference frame index. Encode the reference frame index in this order from 0 to 3. Then, encode it with Unary and limit it to 3 bits. The first bit will have context model 54 plus A plus 2B, where A is 1 if the left macroblock is available and doesn't use reference frame 0, and B is the same but for the top macroblock. The second bit will use context model 58, and the rest will use 59. Next, we'll encode the motion vectors for each partition of the macroblock. We go through each partition in order from left to right, then top to bottom, and if there are sub-macroblocks, we follow the same order for those as well. For each partition, we encode the horizontal X offset first, then the vertical Y offset. The offsets will be encoded in 3 parts, the unary, remainder, and sign bit. For the unary part, multiply by 4 to remove decimals. Get the absolute value, write it in unary, and limit it to 9 bits. The remainder part only applies if our value was greater than 9. Subtract 9, write it in normal binary, and add zeros before until it's at least 3 bits. Then, prefix it with the unary of the number of bits minus 3. Finally, for our sign bit, if our value is negative, write a 1. If it's positive, write a 0. And if it's 0, write nothing. Let's first encode the unary part of our X offset. The first bit will use context model 40, 41, or 42, depending on a few factors. Firstly, find the top and left partitions and get the X of their motion vectors. Get the absolute values and add them together. Finally, Use this mapping to determine the context offset. The next 3 bits will use context models 43, 44, and 45, and the rest will use 46. For the unary part of our Y offset, we'll do the same, except all context models are 7 higher and we get the Y instead of the X of the motion vectors. Finally, the remainder and sign bit will be encoded in bypass mode. After, we'll encode the coded block pattern, change in QP, and residuals in the same way as before. After repeating this for all 3,600 macroblocks, adding the CABAC termination symbol, adding RSBP trailing bits, and the 4-byte size, we have our P-slice. Great job! We figured out our 2 frame types, IDR frames and P-slices. For the rest of the video, we'll use an IDR frame following a cut, and P-slices everywhere else. After encoding the rest of the video, we'll have a long list of NAL units. Now, let's fix our audio. So, we're encoding the amplitude of the left and right speakers with 2 bytes, 44,100 times a second. Each 2 bytes we'll call a sample. Our samples will be 16-bit signed integers, ranging from -32768 to +32767. We'll divide them by 32,768, so they range from -1 to 1. Next, let's group every 1024 left speaker samples and every 1024 right speaker samples into a frame. To make our audio smoother, we'll extend each frame so that each frame contains the samples from the next. For the last frame, add padding zeros to ensure it also contains 2048 samples. Then, we'll fade in and fade out our frames to make them smoother. We'll make a curve that starts at 0, rises to full strength in the middle, and goes back to 0 at the end, using this formula, with n being the sample index. Sine of pi/2048 times n plus 0.5. Next, let's extract the frequencies out of each frame. Imagine viewing it through an equalizer or spectrogram. Imagine we have 2048 samples, a short, wiggly wave. We want to find out, how much does this chunk look like a wave at a certain pitch? To check this, we take a pure sine wave and line it up with our audio chunk. Then we ask, does the shape of our audio chunk match the shape of this pure wave? Let's call the number of waves in our frame k. We will test k values from 0 to 1023. Let's start at k equals 0. Go through each sample in our frame. We will assign a score for each sample, telling us how similar it is to our sine wave. This score is calculated using this formula. Sample value times cosine of pi/2048 times sample index plus 1024 plus 0.5 times k plus 0.5. Then add up all the scores and multiply by the square root of 1/1024. We do this for all of the k values. Now, after that, we have 1024 frequency coefficients for the left channel and 1024 for the right channel in each frame. To find the pitch corresponding to each frequency coefficient, we take the coefficient index, add 0.5 to it, and then multiply by 44,100 divided by 2048. This gives us the frequency in hertz. Our next step is to quantize our coefficients. This is where most of the audio compression will take place. Here we have an audio frame, consisting of 1024 left and right frequency coefficients. We're first going to group similar frequencies together into 49 bands, as defined in Table 45 of the AAC specs. The lower frequency bands have fewer coefficients, while the higher frequency bands have more. This is because as pitch gets higher, the frequency increases exponentially, meaning that while the first 100 coefficients represent a pitch change of over 5.5 octaves, the last 100 coefficients only represent a pitch change of 2 semitones. For this reason, individual coefficients in higher bands are often more quantized than those in lower bands. Here we can see how our frame looks if all bands were scaled equally. Our first step will be to decide the quality of each band. For each band, we will find the average energy and maximum energy using these formulas. These energy values essentially give us an idea of the amount of data within each band. We'll also find the average energy of all 1024 coefficients in the entire frame with this formula. Next, for each band, we will calculate a band quality with this formula. The band quality compares each band with the overall average energy to calculate its importance. Then, it is multiplied by this fraction, which is larger at lower bands and smaller at higher bands, emphasizing the more important low frequencies. Now that we have a quality value for each band, we will quantize the coefficients in our bands with varying accuracy. We will do this by first multiplying the coefficient by a scale factor. The scale factor is determined from this formula. First, we divide the quality by the square root of the band's average energy. Find the log of that, then multiply it by this constant, roughly equal to 13.3. Then, round it to the nearest integer. Finally, to quantize each coefficient k, we will first obtain a variable t using this formula. Then quantizing like so. Before we begin writing our frame, I wanted to let you know that AAC frames can be partitioned and predicted in a way that is much similar to what we did with our video. I won't be explaining them today, but please read the sources I linked in the description for more info. Anyways, now let's begin encoding our frame. Start by writing a 1 using 3 bits to indicate the frame contains 2 channels. Then, using 4 bits, write a 0 or a 1 to indicate the left or right channel. Next, we'll write a 1 to indicate that both channels are using the same settings. Now, we'll encode our channel settings. Start with a reserved 0 bit. Then, write 00 to indicate we're using 1024 coefficients, and a 0 to indicate we're using sign to fade our frames. Next, we'll find the index of the last band that has a non-zero scale factor value. This will be our maximum scale factor band, and we don't have to encode any bands after it. Write this number using 6 bits. Finally, write a 0 to indicate we aren't using prediction, and a 00 to indicate we aren't using the mid-side mask. Now, we will encode our scale factors of each band. We will encode them as the change in scale factor, with the initial value being the first scale factor. Let's write the initial value with 8 bits, so the decoder will know where to start. Next comes our section data, but we'll get back to this later. To improve efficiency, we'll represent the scale factor differences with optimized codes in a process called Huffman coding. These codes are optimized so the more common values get shorter code words, while the less common values get longer code words. For our scale factors, we'll use table A.1 of the AAC specs. To find the code word, add 60 to the scale factor difference and get the corresponding value. Next, convert the code word from hex to binary and cut it to length bits by removing zeros on the left. After the string of code words, add 3 zeros to indicate no pulse data, TNS data, and gain control data present. Next, we'll encode our bands. The coefficients are often small, so let's combine them into groups of 4, or pairs, before encoding with codebooks. In the AAC specs, there are 11 different codebooks we can choose from. To find the best one, let's first find the largest coefficient and set this to the largest absolute value, or LAV. Then, refer to table 59 in the AAC specs. If your LAV is greater than 16, we will use codebook 11. Otherwise, find the two codebooks with the smallest possible LAV to cover all of your coefficients. Then, group into either pairs or groups of 4, based on the dimension of codebook. If unsigned CBI is 1, that means we will only be coding the absolute values, and we'll have to separate our signs for now. Next, we will assign an index to our pairs or quads, so we'll know which code to use. This is how we'll map the coefficients to the index, depending on which codebook we're using. Now that we have an index for each group, we will use the codebook to find the code using the same method as before. Add up all the codes and determine the total bit length. Do this for both codebooks. Finally, keep the code with the least bits. Then encode the sign bits. For each coefficient, encode is 0 if it's positive, and a 1 if it's negative, and nothing if it's 0. If our band has a LAV more than 16, we will use codebook 11. We would first encode our coefficients normally, but with values clipped to 16. Then, after the sign bits, we will encode escape bits. To do this, subtract 16 from the absolute coefficient, then encode this as an unsigned integer. Then, count the number of bits you used, and write that many ones before. Finally, add a 0 to the ones. If your band had more coefficients over 16, simply write their escape bits in order. Now, it's time to revisit the section data. This is where we will store which codebooks we used for each band. We will do this by grouping all consecutive bands that use the same codebook into sections. For each section, we will write the codebook ID with 4 bits, then the number of bands in the section with 5 bits. Finally, we will do the same but for the right speaker. Encode the global gain, section data, scale factor, 3 zero flags, and lastly the coefficients. If our frame isn't byte aligned, add zeros until it is. And that's one frame done. Repeat this for all other frames, and we've finished encoding all our audio. At this point, we have our video and audio information all compressed, but we don't really know how to play them together. How do we combine these into a single file? Well, first, we need a way to store timestamps alongside our video and audio, so we know how to sync them. We also need a way to identify codecs, track counts, and essential metadata like resolution and sample rates. To hold our video, audio, and metadata together, we will use a container format using files and folders. Some files store metadata like codec details and timing, while others hold the actual compressed NAL units and audio frames. This format is what we call MP4. Let's call our files atoms. Each atom will start with 4 bytes of size and 4 bytes of type. We'll start by writing the file type compatibility atom, FTYP, using these values. Size, 32. Type, FTYP. Major brand, ISOM. Minor version, 512. And our list of compatible brands. ISOM, ISO2, AVC1, and MP41. Next, we will write our movie data atom, or the MDAT. This will include the NAL units and the audio frames. First, find the total number of bytes in all our NAL units and audio frames, then add 8. This will be our size. Then, write MDAT. Then, we'll put our NAL units and audio frames in order from which they occur. This means for every 30 NAL units, there will be 43 audio frames in between. Writing our video and audio data in order will allow for smoother playback. Next, we will write our movie atom, or the move. This will store all the synchronization and metadata. Within the move atom, we'll write a movie header, or the MVHD. Set duration to the video duration in seconds, multiplied by our timescale, which is 1000. Now, create 2 track atoms, one for the video and one for the audio. We'll first do the video. Inside the first track atom, create the track header, or TKHD. Then, create the edits atom, or EDTS, and the media atom, or the MDIA. Inside the EDTS, create the edits list ELST like so. The ELST atom maps the segments of media to the track timeline, controlling playback timing, start points, and speed. In MDIA, create the media header, or MDHD. Note that the timescale is 15,360. The duration is calculated using this new timescale instead of 1000. Then, create a handler atom, or HDLR, like so. This identifies our track as a video track. Next, create a media info, or MINF atom. Inside, create a video media header, VMHD, like so. After, create a data info, or DINF atom, and a sample table, or STBL atom. Inside the DINF, add a data reference, or DREF atom, like so. This item lists the data references that specify where the media data for a track can be found. Inside the STBL, add a sample description atom, STSD, like so. Inside this, add the Advanced Video Coding version 1, AVC1 atom, like so. Inside the AVC1, add the Advanced Video Coding Configuration, or AVCC, atom, like so. This atom starts with several fields, then stores our sequence parameter set and picture parameter set. After each set, add a stop bit, or a 1, and zeros to ensure it is byte aligned. Then, add the sample to time, or STTS atom. This item determines the amount of timescale units per NAL unit. Remember that each timescale unit is 1/15,360th of a second, so 512 timescale units would be 1/30th of a second, or 30 FPS. Next, add the sync sample atom, or STSS. This item contains the sample number of each IDR frame. Remember to add 1 to the sample number, because for some reason, MP4 samples start at 1, not 0. Next, add the sample to chunk atom, or the STSC. This item maps the NAL units and audio frames into chunks, helping with synchronization. Each chunk will contain 1 NAL unit and 1 or 2 audio frames, depending on where the audio frame falls within the duration of the NAL unit. Once we get the chunks, we will group all chunks with the same number of NAL units into a section. Then write the first chunk of the section, samples per chunk for the section, and a sample description index, which is always set to 1. After, add the sample size item, or the STSC. This item stores a list of byte sizes for each NAL unit, including the 4 byte size prefix before each NAL unit. Finally, add the sample chunk offset atom, or the STCO. This item stores byte offsets for the start positions of each NAL unit within our entire file. Now, for our audio track, create the TKHD, EDTS, ELST, and MDIA as before. In our MDHD, set the timescale to 44,100 and adjust the duration accordingly. In our HDLR, set handler type to SOUN and name to sound handler. In the MINF, instead of a VMHD, add a sound movie header, SMHD, like so. Next, write the DINF and DREF as before. Let's replace the AVC1 and AVCC with MP4A and ESDS. Write the MP4A like so. Write the ESDS like so. The ESDS contains information specific to our audio. Next, in the STTS, update the sample count and set the sample delta to 1024. Update the sample to chunk, sample size, and chunk offset atoms to the audio frame sizes and positions. And that's it. Our MP4 file is ready to be played. Just kidding. The last step is of course to like and subscribe to my channel. But in all seriousness, if you've made it this far, then I'm genuinely proud of you. You now have a very deep understanding of video compression. Keep in mind that I've left out a lot of information, such as B slices and audio frame partitioning, because there's simply too much to cover. If you want to continue down the rabbit hole, I would highly recommend that you check out the sources I've put in the description. As a recap, we began with arrays of pixels and a list of left and right audio samples. We then divided the pixels into macroblocks, predicted them, extracted frequency coefficients, and encoded everything using CABAC. We grouped the samples, extracted frequencies, grouped them into bands, and encoded it using a codebook. Finally, we combined both video and audio streams into a single MP4 file. To decode the MP4 file, we reverse these steps. To get the video, extract the NAL units, read the slice header, initialize CABAC, decode with CABAC, reconstruct the residuals, undo the macroblock prediction, and convert the data back to RGB format. For audio, Huffman decode the scale factors, get the band codebooks, Huffman decode the bands, inverse quantize, and inverse frequency transform. For more detailed decoding information, please read the H264 and AAC specifications. Both are linked in the description. As always, thanks for watching, and have fun encoding your videos.